We continue discussing about the kinematics of fluid flow and its study. The study, obviously, the question is how to represent it and how do we represent the flow that takes place. So two distinct methods that we have mentioned, Langrangian and Eulerian. In Langrangian method, we follow the individual particles. When a fluid flow is moving, then we have to keep track of each material particle that exists in the fluid. And you can imagine that in a certain mass of fluid or a certain volume, how many millions, billions, innumerable particles may be there, and keeping track of such a motion is not an easy job. However, in some cases, that is important and we need to study that. And the method, it requires us to track the velocity, the acceleration, and other parameters, other fluid properties, pressure, for each particle that is under consideration. And this is not an easy job, quite a difficult thing to track. In some cases we can do that, in others we cannot. And here I give you a small example. For example, if there is a billiard board and you know that there are small balls, they are of a finite number. And we know that the number is not too large. It's manageable, very small. So anytime a billiard ball is hit or we want to keep track of that, it is easy, we can follow it. So this one seems a simple situation, and this is a simple example of where the things are easier to keep track of each individual particles. In this case, each billiard ball. And here also represents that if in a certain mass or volume of fluid, and we take three arbitrary points, the material particles represented by A, B, and C, then at a given time, let's say their velocity is represented, the velocity of particle A is represented by velocity of V, velocity of B is represented by velocity of B, and so on. So if the number is so small, we can follow it, we can see. But if the number is too large, it's impossible to keep track of them. So with the same thing is written here, that with a small number of objects, such as billiard balls on a pool table, it's easy to follow it. But in description, one must keep track of position and velocity of all individual particles. Not an easy job in general terms. So therefore, a more common method that becomes easy is that we consider a mass of volume, a mass or volume of a fluid, and we consider it as a whole, and we just take some particle in the fluid and then just see its movement. And then we assume that its movement, whatever happens to that particle, happens to the whole system, the whole setup. And we call that as Eulerian description of the fluid motion. In the Eulerian description, a finite volume, I mentioned that, called a flow domain or control volume, is defined, through which the fluid flow will move. Instead of tracking individual fluid particles, we just define field variables and see their variation. The field variables at a particular time is the value of the variable for whichever fluid particle happens to occupy that location at a given time. So we take one particle and then the fluid property, the field variable, and normally when we say field variable, we are talking about the velocity, the acceleration, the pressure, and that kind of things, variables that are associated with the movement of the fluid particle. And if we need to write that in our notation, we normally represent it by the pressure field is represented by P of X, Y, Z and T if it depends on time as well. The motion is generally unsteady. But if it is steady, then T will be taken as 0 and will disappear from the equations. The velocity field, however, it does many a times change with time, but it can be fixed as well and not dependent on time, but it does depend on the X, Y, Z direction because it has a motion, it has a component that plays a role in either X, Y or Z directions, the three standard rectangular coordinate system. And the same goes for acceleration. Collectively, these and other field variables define the flow field. The velocity field can be expanded in Cartesian coordinates as, so if we write the velocity v is equal to u, v and w, then its three component. U itself is a vector depending upon x, y, z and time in the x direction. Similarly, the component v is represented as shown, and the velocity, the vector as a whole, is combination of its three components u, v and w. In Cartesian coordinates, we normally denote it as shown.